Meera Hahn, and I will be presenting our paper, Where Are You? Localization from Embodied Dialog. Imagine trying to visit a friend who works in a museum for the first time and getting lost in the new building. Not sure where you are, you call your friend who knows the building quite well. You start describing your surroundings. I am standing on a red carpet looking at a seating area. They may ask you to move or look around. Is there a round table in the middle of the room? So you start navigating in response to their questions and answer them. Yes, there is a wooden round table. After a few or more rounds of back and forth, your friend will hopefully know your location and come and get you. For future purposes, let us call the agent answering questions and navigating the observer, and the agent trying to locate the locator. Success at this cooperative localization task requires active participation from both agents. Specifically, it requires goal-driven questioning from the locator, unambiguous answers from the observer that communicate its observations. Oftentimes, it also requires the observer to navigate, both to investigate the environment and to seek out discriminative observations. In this work, we present Where Are You? Way, a new data set based on this localization scenario. During data collection, we pair two annotators, one who acts as the observer who is spawned at a random location in a novel environment, and one who acts as the locator who is provided a top-down map. In this video, we first see the locator looking at various parts of the map. The map can be seen as a proxy for familiarity with the environment. It is highly detailed, often including multiple floors, but does not show the observer's current or initial location. The observer can navigate within the environment but has no access to a map. To resolve this information asymmetry and complete the task, the observer and the locator communicate in a live two-person chat. The task concludes when the locator makes the prediction about the current location of the observer. For the environments, we use the Matterport 3D dataset of 90 reconstructed indoor environments. In total, we collect 6,000 English dialogues of humans completing this task from over 2,000 unique starting locations. We leverage annotations from around 200 unique workers, and on average, they exchange around 5 messages per localization. On the right is the histogram of localization error of the human annotators, which on average is 4 meters. While 75% of the localizations are within 3 meters, large localization errors can occur when buildings have multiple rooms that look the same. We will show examples of this later. Way is the first dataset to focus on localization. There are multiple vision language-based navigation tasks and datasets, but they all assume the agent is already localized. For example, in VLN, the navigator's location is already known by the instruction-giving agent prior to giving directions. Also, VLN does not use dialogue. The CBDN task does use dialogue, however, the remote agent assumes knowledge of the navigator's location at each step in the dialogue. The Way dataset and the localization tasks we introduce on top of it fill this gap by introducing a dialogue-based means to localize the navigator, which we can see as a precursor to tasks such as VLN and CBDN. Additionally, aside from finding lost friends within a building, we can see the localization paradigm as being applicable to search and rescue settings, where localization models could have the potential to help emergency responders localize callers quicker by identifying locations in a building that match a caller's description. Having presented the Way dataset, I will now talk in detail about the tasks it supports. The combination of localization, navigation, and dialogue in Way provides for a variety of modeling possibilities. We have identified 3 compelling tasks which are fully supported by the dataset. The first task is localization from embodied dialogue. The input for this task is a partial or complete dialogue between the locator and the observer and a map. This input is then given to a localization model. The model solves the state estimation problem of localizing the observer. This task can be evaluated using localization error via Euclidean distance or geodesic distance. Note, this task does not require navigation or text generation. The second task we propose is embodied visual dialogue. which models the observer agent. The input is a partial dialogue, which ends in an instruction or a question from the locator and a first-person view of a navigable environment. These are input to the modeled observer agent, which outputs a navigation action and a natural language message to the locator. The final task we propose is the most difficult and is called cooperative localization. In this task, both the observer and the locator are modeled agents. Therefore, the only inputs are the first-person view of the environment to the observer and the map for the locator. The modeled agents do multiple rounds of turn-taking dialogue when the output, and then the output is a single prediction of the observer's location. The way dataset can be used to warm start and evaluate this task. In this work, we specifically focus on modeling the LED task. We model the LED task as a language condition pixel-to-pixel prediction task using a LingueNet skip model. The input of this model is a dialogue and a top-down view of the environment. We choose to use a top-down map because it mirrors the environment observations human locators had during data collection, allowing a straightforward comparison. During training, we apply standard data augmentation techniques to the visual input. The output of the model is a probability distribution over possible positions from the top-down view of the environment. We adapt the language condition pixel-to-pixel LingueNet architecture to fuse the dialogue and environment representations. LingueNet is a convolutional encoder-decoder architecture. Additionally, we introduce a language-modulated skip connection between the corresponding convolution and deconvolution layers, which we find improves performance, and we call this adapted architecture LingueNet skip. The model outputs a probability distribution over the input top-down map. During inference, the pixel with the highest probability is selected as the final predicted location. We train the model to minimize the KL divergence between the predicted location distribution and the ground truth location, which we smooth by applying a Gaussian with standard deviation of 3 meters, which matches our success criteria. Here we show the percent of successful localizations in the environment unseen by the model during training. We define a success as a localization with under 3 meters of localization error. We use human performance as our upper bound, then report our LingueNet skip model performance. We show that removing the skip connection decreases our performance, as does removing data augmentation. We show that training without the language input or the visual input severely decreases performance. The no language model essentially learns a prior similar to a map of free space in the building, which performs better than the no vision model, which learns a uniform distribution over the output space since it can't observe the map. We also show that the LingueNet skip model outperforms simple non-learning baselines such as picking the center pixel of the environment, picking the location of a random node in the environment, or doing a nearest neighbor search. Here we show the qualitative results from our LingueNet skip model. First, the locator probes the observer for a description. The observer responds with the brief description of the living room with details such as a small round glass coffee table and a blue cream colored floral rug. The locator asks for more details on the rug, and the observer responds to the question and offers more details on the room. The locator seems to know the room in question and starts to ask specifics of the location within the room. Our model is able to ground these descriptions from the dialogue into its prediction and get a localization error of 0.53 meters. Often, failures we see from our model are due to incorrect aliasing of the dialogue descriptions, or sometimes we see an inability to ground the dialogue into sensible places at all. In summary, we have introduced the WAY dataset containing 6,000 human dialogues from a cooperative localization scenario in a 3D environment. WAY is the first dataset to present extensive human dialogue for an embodied localization task, filling the gap of localization in the embodied dialogue literature. We first propose 3 embodied localization tasks, which are fully supported by the WAY dataset. Localization from embodied dialogue, which models the localization, embodied visual dialogue, which models the observer agent, and cooperative localization, which models both agents. We have only presented a model for the LED task, so there is much to be explored in the other two tasks. We use the LinuNet skip model on LED and show it outperforms simple baselines and model ablations, but we have not fully explored the potential of this task. For instance, we use a top-down map, but for future work, this does not need to be restricted to this choice and may leverage RGB panoramas or 3D reconstructions that the Matterport 3D provides. Additionally, there is a need for a more sophisticated dialogue encoding. Thank you for listening to our talk. To learn more, please check out our code and our project webpage.